Okay, so try to do things a little bit differently. I don't know if I'll always be in my office doing this, but this kind of second lectures for this week, um, I've got some webcam available as well. So we left off thinking about, how do we build confidence intervals for sample means and sample proportions, or sorry, using sample means and sample proportions for the true population mean and true population proportion. Now, one thing that I mentioned at the time and when I was talking through part of the Excel in the Excel video is it's kind of goofy to think about how do I not know the population mean, but I somehow know the population variance. And I try to describe it away with, well, sometimes we know that just like the machinery has a certain amount of variance on what it produces, and so maybe we do know that. But more likely than not, we don't know what that population variance is. So most of the time, all we have is this sample variance. So instead of being able to come up with this standard deviation of our sample means when we know the population variance, we can still come up with that, but we're going to have to use the sample instead of the population variance. Right? Like it looks ultimately the same once we plug the numbers in, but we have to treat things a little bit differently because this sample variance, remember we divide by n minus 1 as opposed to n, so you can almost think about even if we had the entire population, we wouldn't really have a perfect measure of what that standard deviation is in our sample means. So because of this, we're going to have to use not the standard normal distribution when we convert things into z-scores. Now when we convert things into z-scores, or we're building confidence intervals, we actually would have to use the student t-distribution. We're not coming up with a z-score anymore, we're coming up with a t-score, if you call it that. Okay? So the student t-distribution is not one distribution. I probably quite often leave off the s on accident, but it's multiple distributions. It's a family of distributions. So it's very similar to the standard normal distribution. They'll all still have a mean of 0, but we won't have a variance of 1 anymore. They're going to be a little bit more spread out, right? And how much more spread out they are will depend on something called our degrees of freedom, which is directly linked to what our sample size is. You can kind of think about it maybe as to why. Well, if we're dividing by n minus 1 instead of n, that matters a lot less if we have 1,000 observations as opposed to 30, right? And so each student t-distribution will be a little bit more spread out. As we get higher and higher sample sizes, it's not as spread out. So as the degrees of freedom goes up, this becomes more and more like a standard normal distribution, or it becomes a close approximation. In fact, at a certain level, you won't be able to distinguish the difference between them even out to like the 4th or 5th decimal point. So what are some of the student t-distribution properties? Well, I already mentioned a few of them. It's symmetric around, so its mean is equal to its median, and that mean is 0. Right? So it's a little more spread out, so the standard deviation is greater than 1. But as we get degrees of freedom that are really high, it converges to, or is a very close approximation for that standard normal distribution. Okay? So in practice, and we'll kind of show you this student t-table. I think I have it here. In practice, once we get down to degrees of freedom over 1,000, right? This last line, infinity, if we could get to a degrees of freedom of infinity, what we would actually have is a standard normal distribution. So these are actually the values that would come from a standard normal distribution. And you kind of notice even over 100, they're looking very similar, right? So in practice, I'll give you examples. I'll either give you something that's way more than 100, and if it's well over 100, you can just use the standard normal distribution to approximate it. Right? So how do we use this table? So just like yesterday when we were looking at confidence intervals, sometimes we want a certain area, maybe in our tails, right? So a lot of the values we were using in the other recorded lecture I had was like we had alphas of 0.1, 0.05, and 0.001. We would then divide those by 2. It's going to be a similar idea when we're using the student t-distribution. So here, this alpha in this table, you can kind of ignore. If it helps, cross it off. All these represent are the area that's in that tail. Now, alpha, when it comes to confidence intervals, we said was the total area in like both tails, on both sides of the confidence interval. So whatever area that you want in one tail, that's what these represent. Well, let's say I wanted 0.05 in each of my tails. I'd look up 0.05, but then the next thing I have to do is, okay, well, it depends what t value now, instead of a z value, what t value would give me 0.05 in the tail depends on what my degrees of freedom is. Okay. So we can think about why, and I'll probably switch here in a second. So let's look at these three distributions, right? If I were to use, let's say I'm trying to build confidence intervals, and the area I want in each of my tails is, I think this one should be 0.025 in each tail. Well, the value from a standard normal distribution that gives me that, so this black line is the standard normal distribution, would be 1.96. So the area to the right of 1.96 here under the black curve is 0.025. Well, notice if I only have degrees of freedom 5 and I don't have the population variance, so I'm using student t distributions, notice the area under that green curve to the right of 1.96 will be something much higher. It's no longer that 0.025 that I wanted. So I'm going to have to, instead of 1.96, I would need a higher t value, right? Because as I get a higher t value, that would decrease that area and it would make it closer to 0.025. If we actually look at the numbers, in fact, right, it's way higher. If we only had degrees of freedom of 5, the area to the right of 1.96 is like 0.068. Okay? So I kind of have the table here. I've already shown you the other table, but if you wanted to cross off that alpha, so if we go back here, you could cross this off and just write area in the upper tail, right? And then we would kind of have something that looks more similar to this. Okay? And I already mentioned, if we go down to that last row, when the degrees of freedom is infinity, those are the values that we would find. 1.96 from a standard normal distribution, the area to the right of it would be 0.025. Right? So that's how we're going to use this table. We'll walk through some examples. I'll keep switching back and forth the table and probably do some board work as well. So confidence intervals, when we don't know what that population variance, or we don't know what that population standard deviation is. So if we collect samples and we want to build this interval, we'll still build it around that sample mean. Right? And I think grammatically, technically, I shouldn't say this is the building a confidence intervals using this sample mean. So this looks really similar to what we did yesterday. The only thing that changes is this now is slightly different, right? Because we can't use the population variance when calculating this. We only have the sample variance. And also, instead of using a z value, we'll use the t value. Now we still divide alpha over 2 because alpha is the area outside of our confidence interval. So we want half of it, on each side. But everything else shouldn't be too bad. And we already know all these other components. So let's see if we can. Oh, I've got an old drawing from a different class. You guys don't want to see supply and demand probably. So if we want to think about making this connection, so I could write my confidence interval equation like this. This guy here represents the standard deviation of those sample means. Well, this is exactly what we did yesterday, except for we were using a standard normal distribution instead of a student t, because we were able to use that population variance. Right? And then this represented the standard deviation of our sample means when we knew the population variance. We also had sample proportions, just so we can see them all right next to each other, where this last part here represents the standard deviation in our sample proportion. So it's all really following the same format. It's just a couple little things are different between these three types of examples. Okay, so how do we solve this? The steps are the exact same we were doing yesterday. It's just now we've got a sample variance at this step. We have a student t instead of a z distribution or standard normal distribution here. And, you know, those two things will be reflected in our equation for the lower and upper bound. So let's do an example. So this is not a great example, but just to put some numbers and see how we would work through this. So let's say we take a sample of 36. We know that, and once we have those 36 observations, we calculate the sample variance and the sample mean. That'd be pretty easy to do in Excel, right? If I had 36 observations, I could use equals average, equals var.s. I get my sample variance and my sample mean. If I want to build a confidence interval that corresponds to an alpha of 0.01, so what would the confidence level be for an alpha of 0.01? Well, 0.01 is the area outside my confidence interval, so the area inside it's 0.99, 99%, right? 99% confidence level. So identify what I need, my sample mean, sample size, sample variance, and we were given alpha here, so it's a little bit easier. What would my t-value be that I need? Well, my alpha is 0.01, so I need the area in each of my tails to be 0.005, and my degrees of freedom would be 36 minus 1, so 35. So I go to the table, I wanted 0.005 in that tail, and my degrees of freedom was, scroll down here, 35. So the t-value that would give me that area in the tail, or the probability I see something more than 2.724 standard deviations away from the mean, that probability would be 0.005. So this is the t-value that I need. So 2.724. Oh. All right. Or 2.72 if I round to that second decimal, just to make the display easier. I could calculate my intermediate step, so I plug in, find what that standard deviation is on my sample means, and now it's just a matter of plugging everything into that equation. Now notice, I didn't write this right here. This represents the standard deviation of my sample means, right? But I could have kind of just plugged those values in as well. I'm just kind of trying to give you, see it written multiple different ways, because we can write it a couple different ways and it really means the same thing. Technically, we don't have to do step 3. We can just plug the numbers in here. But I think for a lot of people, it makes more sense to do this step, and it just kind of helps make it more clean. And once you get down to this point and you're entering things in your calculator, there's just a lot fewer numbers that you have to deal with, right? So this is how we would build the lower and upper bound, right? We can still think about this as our margin of error. I'm just going to, like I said, the terminology is really just supposed to be used with proportions, but for us, it helps always call it margin of error here. You subtract to get the lower bound, you add to get the upper bound, right? So that's how we do it. Pretty similar to what we did yesterday. Let's work through a different example. So let's say American Medical Association says, well, look, be a physician. You can make $175,000 on average. You're unconvinced, so you take a sample of 81 physicians, and you find that from these 81, that a sample mean of 160,000 and a sample variance of 324 million. Right? So what would the confidence interval be for that sample mean, or sorry, using that sample mean, if we wanted to build a confidence interval for what the true population mean was at the 95% confidence level, right? Or an alpha of 0.05. Remember, 0.05 is the area outside the interval, 0.95 was within, so the 95% confidence interval. Well, one thing we talked about yesterday is which of these can we rule out? Well, if we're looking here, it looks like to me 160,000, unfortunately, right in the middle of all of these, so there's really not one that we can rule out here. Right? We said whatever the sample statistic we find is, in this case sample mean, it should be exactly in the middle of our confidence interval. So how are we going to kind of work through this one? Well, we identified the information that we have, right? What was the t-value going to be that we need? Well, we had a 95% confidence level, right? So the area outside of the interval in decimal form, or alpha, was 0.05. But we have two tails, so the area in each tail will be 0.05 divided by 2, so 0.025. Our degrees of freedom, I believe the sample size was 81. So n minus 1, 81 minus 1 is 80. We go down here, 80, t-value that would give us the area we wanted of 0.025 is 1.99. So we go back, 1.99, do the intermediate calculation. Now if you're kind of following along doing this, don't put, you can't use 324 here, you need to put all the zeros in. And then it's really just a matter of plugging everything in, right? So here's our equation. Subtract our margin of error for the lower bound, add it to get the upper bound, and we find the confidence interval for where the true population mean starting salary for physicians would be to be between $156,000 and $164-ish thousand, right? So how do we use this confidence interval to make some interesting, decisions? Well, the AMA said the average was 175,000. With 95% confidence, I can tell them that is not the true starting salary, right? The true starting salary is one of the values in between our lower and upper bound, and 175,000 is not in that. Right? So these are kind of the slides that go along with the Excel. If you're just wanting some kind of like all the equations in one place. But the one that we really haven't, talked too much about, because we've used the norm.s to INV, is really you're just replacing anytime you need to use the student t-distribution, you just put t dot instead of norm.s dot. Right? So I talk about this in the video file of doing the work in Excel, but these slides kind of put all the information in one centralized location as well. So hopefully this lecture was a little bit better. I can kind of use the board. I know it was shorter, but my goal is in the future to use more of this format now that I have figured out OBS software where I can switch back and forth between different sources to make it a little bit more continuous. Once again, if you have any questions, please email me. I see some of you have already started viewing the Excel help video on YouTube. I will continue to post these lectures to YouTube. And next week it should be on Monday. I should be recording them on Monday and getting them posted. All right.